Let's turn to an important theorem called the Cauchys theorem. It states the following, that if a function f is analytic at all points interior to and on a simple closed contour C, so this is a simple closed contour, it's not intersecting with itself, and it starts and ends at the same point. If this is the case, so it's analytic at all points interior to this curve, then Cauchys theorem tells us that the integral over this curve of f of z is equal to 0. So here we have an example of a contour which is not simple closed contour because it's intersecting with itself. So we cannot include this kind of contours in Cauchys theorem. Here is a concept which is also often used. It's the concept of simply connected domain D. You know, a domain is an open set which is connected, but a simply connected domain is a domain such that every simple closed contour within it encloses only points in D. A domain that is not simply connected is called multiple connected, and this may sound difficult, but it's not difficult at all. This is an example of a simply connected domain, because any simply closed contour like this, for example, only contains points in D which are members of D. So it only encloses points. It encloses only points in D. It's easy to understand, or maybe more easy to understand the definition by finding some counterexample. Here is some counterexample of a simply connected domain. If we exclude this black part from D, then just look at this simple closed contour. It does not encloses only points which is inside D, because the points here is not contained in D. So this set D is not simply closed, simply connected, sorry. And the following theorem tells in fact it's very simple to derive this theorem from Cauchys theorem. It tells the following: if a function f is analytic throughout a simply connected domain D, then this integral is equal to 0 for every closed contour C lying in D.